it should be a kind of review of what you saw in undergraduate quantum, more or less. We're doing sort of one-dimensional wave mechanics problems. So the one-dimensional, time independent Schrodinger equation. That's kind of the name of the game for us. And just to remind you what that is, that's we have our Hamiltonian, which is the kinetic energy, which gives us two derivatives here of the wave function. And then there's some potential. We'll look at various potentials, and we're looking at eigenvalues of this equation. This is the kind of thing you practice on your homework for this week. This is essentially the same as saying you have some operator A, it's acting on some psi, except it's, instead of a vector, you have a function because we're in the space L2R. That's our Hilbert space. And you're looking at, eigenvalues of this differential operator. So for us, the A is this Hamiltonian operator, which is a kinetic plus a potential energy. And it's just a differential equation. You just have to solve it. There's not much more to it. And you can solve it for different kinds of potentials, which is, sort of what we're going to be doing. It's convenient to kind of rewrite this to get these derivatives out by themselves, just because it sort of makes it a little bit cleaner. So if you have the derivative by itself, then you can sort of rearrange things, right? You can multiply by 2m over h bar squared. And this like 2m over h bar squared runs around everywhere, and it's, E minus V. This kind of quantity is quite common is quite common in what we'll be doing. This E minus V times this quantity here, and all of this is of course multiplying psi, and then all of that's equal to 0. So this is the kind of thing that we're going to try to solve. And we're going to look at different potentials, right? And in general, you have your potential. And we'll look at different ones. Usually, we look at piecewise potentials, like a potential barrier. And the V can have discontinuities. So it generally has some piecewise constant type portions, and then it jumps. So here's like a square barrier potential. And so it can have these jumps. That'll be okay. Of course, we'll also look at, different ones. Here in blue, we'll look at harmonic oscillator potential, which is, a parabola type deal. And the question is, for these ones with discontinuous jumps, what happens, here at this jump here at x0? Well, you have to be careful, and you can use the Schrodinger equation to sort of figure out what happens around these jumps in the potential. And a common thing to do when you have any kind of singularity like that, or jump discontinuity, is you just integrate around this discontinuity, and you just see what the equation tells you. So what the equation tells you is you integrate from, x0 minus a little bit to x0 plus a little bit. When you integrate the second derivative, of course, this is the fundamental theorem of calculus. This is just going to be the first derivative. The integral kills one of the derivatives, and you get the first derivative evaluated across that discontinuity from, x0 minus epsilon to x0 plus epsilon. So it's just the difference in the first derivative across that jump. And this should be equal to the integral across the jump of, you know, the 2m over h bar squared v minus e, right? And if we think about this, right, there's no derivatives here. So what happens here is that we have to, this v will change, you know, from this value to this value across the jump. And so we just have to be careful that that everything works out here. And so if there is a jump, right, then of course that doesn't change the integration, right? It's even if this has a jump, if we integrate across this discontinuity, then as we make epsilon smaller and smaller, right, the region of integration gets smaller and smaller, and so this should approach 0, even if there's any kind of discontinuity in the potential. Because if you think about the area under this curve, right, it's not going to, it'll, you know, vanish. As long as v doesn't, you know, shoot off to infinity or something like that, you're safe. So for solutions to the Schrodinger equation, both psi and the first derivative of psi with respect to x have to be continuous. They can't jump. And oftentimes what you do is you, since both of those have to be continuous, then the following quantity is also continuous, the derivative divided by the function itself. And this is called a logarithmic derivative, because if you take the derivative of the log of psi, that's just the derivative divided by the function. So sometimes it's nice to use this as a condition. So we'll use this kind of thing as a matching condition. And so basically, what do we need? We need to know the solution for these constant pieces. And then we can use the continuity of psi and the derivative of psi in order to match them across any jumps of, say, like a piecewise constant potential. Any questions about that? So this is the kind of matching that we have to do if we have jumps in the potential. So, yeah, any questions? We good? So what about the constant piece? How about in this region, what's the solution? Well, in that case, v is a constant, and so this whole thing is a constant, and we might call this, you know, we could set this equal to 2m nu over h bar squared if we wanted, where nu is this e minus v piece, where v now is a constant. So that's in the constant regions. And the solution to that, it's just you know, a simple ordinary differential equation. It's two derivatives acting on psi is equal to minus 2m nu over h bar squared psi. And here the solutions are going to be exponentials, either complex or regular. And so there's two cases, right? There's two cases here. There's when nu is bigger than 0, it's positive. That means the energy is bigger than the potential. And immediately you should think the energy is bigger than the potential, then the particle should be moving around, right? It's got it's got some positive kinetic energy, right? If the total energy is bigger than the potential energy, it's got some kinetic energy. So you should immediately think, oh, well, I should have some kind of momentum for the particle, so I should get exponential solutions. And indeed, that's what you get. You get oscillations in the wave function. You get two, solutions here: a e to the I square root of 2 m nu over h bar x, and then you get the other solution is two derivatives, so there's two unknowns in the solution. And how can we think about these solutions? Well, this is telling us that there's just some constant kinetic energy, right? So there should be some momentum associated with the particle, and it's just moving in a flat potential. So the potential doesn't do anything. It just tells you what the kinetic energy is. It's the total energy minus the potential energy. And so there should be two different kinds of particles that have that kinetic energy, right? It's ones that are moving to the left and ones that are moving to the right. And that's what you get. You have the ones that are moving to the right and ones that are moving to the left with two different momentums, plus or minus, to the left and right, square root of 2m nu here. Right. Yeah, so that's, and, in the homework, you're looking at eigen functions of differential operators. And these are the two eigenfunctions, right, of this differential operator, where, this piece is a constant. And you have two possible vectors, right? So that means you have two degenerate, you have a subspace here spanned by two eigenvectors, right? It's a two-dimensional subspace. Why is it two-dimensional? Because there's two different kinds of particles that, two different kinds of states of a particle, right, that satisfy that energy, just a constant kinetic energy. Again, it's either a particle moving to the left or right. So that's what you get. Kind of similarly, if nu is less than 0, then you have, then this whole thing becomes positive, right? And in that case, you get exponential increases and decays. And that's not a classical thing. You wouldn't get that classically, right? If you have, you don't ever consider the case classically where the total energy is less than the potential energy, right? Because it would correspond to negative kinetic energy. It would be nonsensical. But in quantum mechanics, it's perfectly fair to consider such things. And in that case, psi of x, it develops exponentially decaying and growing solutions. So instead of oscillations, you get exponential decay or growth. And so you can write that as 2m magnitude here of nu, right, x over h bar plus b e minus square root of 2m magnitude here of nu x over h bar. And again, we get two different fundamental solutions because it's a second order equation. So you have these unknown coefficients, and these are the things that you need to match using these continuity things. This helps you find A and B, as we'll see when we do some examples. Any questions though about that? These constant piecewise type things.
Do we just write down the expression for psi? Are we going to derive it, or we just guess that out of intuition that it should be exponentially growing or decaying?
I don't, I mean, I assume you've solved this differential equation before. It's just, yeah, it's this differential equation, d squared f dx squared. It's the most standard differential equation, I think, in physics. I'm not, I mean, yeah, I'm not sure what there is to derive necessarily. I mean, yeah, I mean, guess and check is probably the the most straightforward way, right? We need two derivatives to give me a factor of lambda times the function itself. The only functions that do that kind of thing, where you take a derivative and you get back the function itself times something, is a exponential. But you need two derivatives to give you a factor of lambda. So the solution to this is always, you know, e to the e plus or minus square root of lambda x. Those are the two solutions. Take two derivatives, you get lambda back. Now, the square root is tricky depending on whether lambda is positive or negative. If lambda is negative, then we could write this as e to the plus or minus I magnitude lambda. Otherwise, you know, or sorry, we can put a minus sign here if you wish. Then the general solutions would be with the I attached here already, because two factors of I will give you the minus sign. Yeah, I'm not sure. Is there something else you wanted me to show with that? I don't.
No, I can see it now, because I was thinking like how would the if we are to solve this equation, how would the solution differ based on only nu is positive and nu is negative? But now I can see that there is a factor of I that can come out, and then
Yeah,
sign.
it's just because of the square root, and you could write this whole thing just as the square root, and then depending on whether lambda is positive or negative, you could pull out another factor of I if you wish. Maybe that's a nicer way to do it. I don't know. There's no reason to break it up into these two cases. Not really. It's just that they represent different physical situations, where here it's sort of, you know, positive kinetic energy, and here it's negative kinetic energy in a sense. And these are sort of non-classical solutions in some sense. They represent like tunneling. Then I thought it'd be nicer to break it down, but no, I mean, you could just write that, you know, the solutions in general are plus or minus I square root of lambda times x. And then depending on whether lambda is positive, then you have this I. If lambda is negative, then another I comes out, and you get I times I is equal to -1. So then these signs reverse or whatever, but you know, it's still the same two solutions, plus or minus, you know, the square root piece. Okay,
Okay.
is that good?
Yeah.
Okay, great. All right, so we have that. So let's see, what else? Typically, you also need to think about the physical situation involved in one of these problems. So let's do an example of, say, a potential step. Say we just have a single step in the potential. And this is some V naught up here, and then this will be 0. So this is V of x. And then you also have to specify which energy we're going to look at. And remember, that's the eigenvalue, and we can look at different eigenvalues, and those will correspond to different solutions, different eigenvectors, eigenfunctions of the Schrodinger equation. So here's the energy. So we put it here. You know, immediately you have to think, like, what's going to happen here to a particle with this particular energy? Well, out here, it's got a positive kinetic energy. So there'll be two solutions, one in which sort of the particle moves this way, and one in which the particle moves out that way. And this is, you know, the e to the IPX over h bar type solution. This is the minus IPX over h bar. And then what happens in here? Well, in here, You have to get a sensible wave function. We know that in here, at least classically, the particles should just collide with this barrier and get reflected back, right? And so it shouldn't even be hanging out in here at all. And so in quantum mechanics, we have to be sure to use the right set of solutions, because in general, we're going to have exponential decay and growth in that region because, E is less than V naught. But you only want to pick out the exponentially decaying solution, because that's the one that makes physical sense, right? What should happen? Well, the particle should come in here and get reflected, but it might penetrate into this potential barrier a little bit. And so it might have some probability of being inside the barrier. That should decay pretty quickly, right? It should definitely not blow up in here. And so you should pick the exponentially decaying solution in here. And so if we think about these A's and B's, then so let's do that. So let's think about what the solution is. So out here, the solutions are, and let me not write P over H bar and then have these H bars. Remember that I can define K is equal to P over H bar. That's sort of more convenient. So in here, out here, the solution is, A, e to the I kx, and B, e to the minus I kx. And out here, the solution is some other coefficients, C e to the minus, instead of K, I can write kappa, which is just the same as K, except that it's the value of E minus, how should I say this? So these guys right here are either going to be K squared, if nu is positive, or if nu is negative, then it's minus kappa squared. So then the minus signs. So then, we can define a positive kappa.
Wait, could you restate the sentence you just said before that? You
well,
said
let me just write it here. So these solutions, okay. I can also write them as right. Let me introduce a new notation then. I can just write this as psi of x a e to the I kx plus b e to the minus I kx, where k is the square root of 2m nu over h bar business. And here, I can do the same thing. I can write this a e to the now kappa x plus b, and they're different. The difference is that there's the difference between whether you do E minus V, essentially. But I guess if you put little magnitudes on here, then it's okay. Then they're basically the same thing. Yeah, where the difference here is that this kappa is square root of 2m, absolute value of nu. So, there's this, if this nu is negative, you have to put negative nu here to make it positive, and here there's no absolute value, so there's a little bit of a difference, but it's the same. It's just you have to make sure that kappa and k are both positive numbers. So it just involves either doing E minus V or V minus E, whichever gives you the positive answer. That's the one you use. And so we reserve kappa for the cases where the solutions are growing exponentials or decaying exponentials. And we use K because that's the thing that corresponds to a positive kinetic energy, particle moving around. So it's just rewriting these solutions, either this one or this one. Does that make sense?
Yeah.
But as I think Anik pointed out, it's all the same differential equation. It's just how you interpret this lambda. If it corresponds to the exponentially growing decaying solutions, then we call it kappa. If it corresponds to particles moving with some momentum, then we call it K. It's just to make the physics a little bit more obvious what's going on. But mathematically, it's the same solution. Mathematically, if you're thinking in terms of complex numbers, then this solution here that's exponentially decaying is the same essentially as these oscillating solutions. It's just, you know, the physics is quite different. So you have these guys, right? And we introduce new coefficients C and D because we're solving this separately out here. And now you have to do some, you have to introduce some actual physics of this problem. So again, this is the time-independent Schrodinger equation, and in reality, we're imagining a situation where we're sending a particle in and it gets reflected by the barrier, and so we're looking for solutions that would tell us about that situation. And we know to do that properly, you'd have to solve the time-dependent Schrodinger equation, put everything in a wave packet. And we'll see the connection between this solution here and the wave packet a little bit later, probably second semester mostly, but we can still sort of use physics intuition to throw out certain pieces of this solution. So the first thing to do is recognize that this guy should be 0 because we don't want solutions to blow up out here at infinity. Here, the particle shouldn't exist. No particle should be here, out here at infinity. Here, we imagine this guy. This is a particle coming in from infinity, from the left out here, right? It's just coming in with some constant momentum in this direction, like we're shooting it in. So that's kind of up to us, right? We're the ones shooting the particle at this barrier. And so there's a kind of arbitrary choice in the normalization of the incoming piece of the solution. And so, this is the incoming particle. And so we're allowed to fiddle with that because we imagine there's some source of particles out here that's shooting particles into this barrier. And we can just normalize it such that A, is equal to 1. We're allowed to do that. And so then the B part, the thing that corresponds to this guy coming out, that must be the reflected particle. Must correspond to the reflection off of this barrier. And then the exponential decay, the C is tunneling. It's the probability that the particle kind of tunnels into this barrier, which is, not accessible to it classically. So that's kind of the physics of it. And now we can, go about trying to solve this thing and kind of see what we get. So what do we get? Let's do continuity, right? Okay, so let's put this at x equals 0. That's also kind of convenient. So let's do here continuity at x equals 0. That'll tell us, right, that what? Well, at 0, this is a plus b. So it's a plus b, which I know is 1 plus b. That should be equal to c, right? Because this we're setting to 0, so there's only c left over. And at 0, this is, like that. All right, what else do we get? We get, as I said, it's useful to look at the logarithmic derivative, which is this guy. And this guy is, let's see, what is it? So if we do it over here, what do we get? We pull down a minus kappa c e to the minus kappa x divided by the function itself, which is c e to the minus kappa x. You see, it's so nice because, this stuff cancels, right? So in one region, it's just minus kappa. How about the other region? In the other region, it's this guy, a plus b. So what do we get here? Let's see. We get ika e ikx, right? And we get minus ikb e to the minus ikx. That's the derivative divided by the function itself, which is a e to the ikx plus b e to the minus ikx. Okay, more complicated, but it's not so bad because we're gonna make sure it's continuous at x equal to 0. So we evaluate this at x equal to 0. And what do we get? We get ik a minus b divided by a plus b. And that should be equal to minus kappa. And of course, a is equal to 1. So we're making some progress here. So let's see. Since a is equal to 1, then we know that ik 1 minus b over 1 plus b. And that's also ik 1 minus b well, no, let me just write down the two equations, right? So you got this guy, 1 minus b, 1 plus b is minus kappa. And you have b is equal to c minus 1. So you have two equations and two unknowns. And you can declare victory because that means there's going to be you've found all the unknown coefficients. That's how you know that you're done, is you apply the physics in the blue, right? Then you apply the boundary conditions here in the red. And in the end, you get, you should get as many equations as you have unknowns. And then you're done. You know, you can just solve the equations, you know, plug them into Mathematica, whatever. You just do some algebra, you know, you rearrange these b's, and you can solve this equation just for b, this top one. And in the end, you get your two solutions. One is for b, and that's, you can find it's minus kappa plus ik over kappa minus ik. And for c, you get minus 2ik over kappa minus ik. And what's interesting is the following. Let's compute the magnitude of b. What's the magnitude of b? An easy way to do that is to compute it squared, and then you can take b times its complex conjugate. It's an easy trick to do. The minus sign here cancels. What do you get? So for b, you get kappa plus ik over kappa minus ik. And here you get the complex conjugate, so you just flip all the i's, right? And then, you know, we got these things cancel, and that's equal to 1, which is also equal to a. What's it mean? Well, it means that, remember that we were looking at probability currents, right? And we found that the probability current for like a plane wave like this was just, you know, the magnitude of the plane wave squared times well, the momentum over m, where the momentum is you know, h, or let me just put h bar k. So what's it mean is that, and this is the same for both a and b, because, you know, they have the same momentum there. It's just one is going to the left and one is going to the right. So it means that the probability flux of the incoming guy, A, is the same as the probability flux of the outgoing guy, B. So it makes perfect sense, right? What happens here? However much flux you put in, that's how much flux you get out. And what happens in the meantime? Well, the particle penetrates a little bit into here. It tunnels in a little bit and then changes directions and comes out. And you should, you know, it should make sense. All the particles that come in, they have to come out. So then what's the rest of it? What's like, what does the tunneling do? Well, because it has to tunnel in there, right? It introduces a little bit of a delay in the time it takes for the particle to get reflected. And we already know that because, so the reflected portion, right? What does it look like? It's BE to the minus IKX. And we saw that the magnitude of B is 1. That's fine. So all this can be is a phase, right? It must be e to the I phi. That's what it's the only option. And the phase is just given, you know, we can take the arguments, we can find the phase of this complex number, and that's phi. And so this is what it looks like. And if you remember when we looked at wave packets, and it's going to be put a little I. When we looked at wave packets, we saw that any wave shift, any phase shift like that corresponds to a time delay in the wave packet. If you go back to those notes, and the time delay is given by h bar times the derivative of this phase function with respect to the energy, or if you want with respect to, you can rewrite this as with respect to the derivative with respect to k, because E here is just kinetic energy, so it's, you know, h bar squared k squared over 2m. So if we were to do the wave packet analysis of this, what would we find for the solution to time-dependent Schrodinger equation? We'd find that a wave packet would come in here, it would get reflected, and none of it would, you know, go off to infinity, so everything will get reflected back. But because of this little tunneling effect, there'll be a little time delay in the time it takes for it to turn around, you know, as soon as the particle hits here. And you can get what the time delay is actually from the time independent Schrodinger equation by calculating this phase shift in the B coefficient. We'll look more on that later when we do scattering a little more formally in the second semester, but this is the first kind of teaser, I guess you could say, of this. Okay, any questions about that? No? Good?
Yeah.
Okay, great. So, so we're looking at these solutions here with E kind of below this V naught, but you can imagine now, let's imagine what happens if we take this and we sort of start pushing it up a little bit beyond the barrier. Well, then as soon as E crosses this threshold, right, you all of a sudden start getting a positive kinetic energy. And so you immediately you can immediately sort of guess that the situation will be a little bit different. You get a different kinds of solutions here, right? If E is up here, well, all of a sudden you'll have your incoming portion, but now the solutions out here are also outgoing and incoming waves. And here we have incoming and outgoing. Now they're oscillating, you know, the E to the I K type waves, but you have a different K here, right? Here's the kinetic energy here, right? This is the kinetic energy. It's the difference between you know, the total energy and the potential. Here you get a bigger kinetic energy here. So this is associated with some K prime, and this is associated with some K, the kinetic energy, the wave vector associated with having that kinetic energy. And now, and the physics now is what? Well, we're gonna set this part of the wave equal to 1 here. Here's the reflected part, that's still our B. C now becomes, you know, C to the E to the I K prime X. That's going to be the transmitted portion. Right now, instead of tunneling, you know, and getting exponentially decaying solutions, you get the oscillating solution. So those are moving particles. So you get a portion of it gets transmitted. Now, what about this guy? This is D to the minus IK prime X. That solution is going to be corresponding to incoming particles from, out here, right? If we had a source out here shooting particles in. So for the same reason that we, not the same reason, but so using physics considerations that, we shouldn't have any source of particles out here, we set this equal to 0. No incoming particles from out at infinity. We're imagining shooting in particles from x, minus infinity, and seeing what happens as they get reflected off of this little step. And now, again, we do the boundary conditions in red. The boundary conditions. Continuity, again, gives 1 plus b is equal to c. And now, instead of, I'm not going to work out the details here, but I can assure you that it's exactly the same as this kind of thing, where you take the logarithmic derivative, except instead of minus kappa here, which we had for the exponentially decaying solution, now we just have, a plus I k prime instead. And so the continuity for the logarithmic derivative tells you that I k prime is I k 1 minus b over 1 plus b. It's identical really to what we had before. I can even show you the other one so you can kind of compare. Instead of minus kappa x, you have an I k prime x. So this becomes just I k prime. That's this guy. And then the other side is the same. So it's still I k a, which is 1 minus b over 1 plus b. Exactly the same, but different. The physics is quite different, right? Now we don't have tunneling. Now the particle gets transmitted through. Now, and now this is, again, 2 equations, 2 unknowns. Again, you know what k prime is because you know what this tells you the kinetic energy. The kinetic energy k is always, h bar squared, k squared over 2m, and the kinetic energy in this case, is always E minus, the potential. So, and this is either k or k prime, depending on how much kinetic energy you have. Here we have a little small kinetic energy, right? Again, just reiterating the physics, and this is large. Okay. So yeah, 2 equations, 2 unknowns. You can solve it, and you get b is equal to k minus k prime over k plus k prime. And now the magnitude of this is not 1, because a portion of the flux gets transmitted through. And you can actually calculate how much it is. You can calculate the reflection probability by just calculating the probability flux ratio. You just calculate the probability flux of the incoming, of the outgoing. Right. You calculate the flux of the reflected portion divided by the flux of the incoming portion, and we know that the kinetic energy out here is the same. So all this is just the magnitude of b squared divided by the magnitude of a squared. This is just, we set to 1. We can always do that normalization. So what we just get k minus k prime over k plus k prime squared. Does it make sense? Sure, because look, if k is equal to k prime, then there's no reflection. What does that mean? That means that it's as if there's no potential there at all, right? No step in the potential whatsoever. So then nothing gets reflected, everything just gets transmitted through. And otherwise, you'll get some portion that gets transmitted and some portion that gets reflected. So that's how that works. And in general, that's how all these problems work. You set up your energy, then you look and see if the potential is bigger or smaller than your energy. And when the potential is bigger, then you know that the particle is tunneling into there. So you have the exponential solutions. Otherwise, the particle has some positive kinetic energy, and so it's moving around. So that's the physics of it. And so these are kind of, this is like baby scattering. And the other kinds of solutions we'll worry about are bound states. But before I mention that, are there any questions about this?
Can you summarize the physics in that picture? The second one, when E is larger than V naught.
This one.
Yeah. What's happening here? Can you just, summarize the whole thing?
Yeah, so yeah, what happens is you have an incoming particle that comes in here and it encounters a potential step. So its potential energy, increases as soon as it hits x equals 0. And correspondingly, its kinetic energy must decrease. So it slows down. And in quantum mechanics, any kind of slowdown like this will lead to some probability of the particle getting reflected back. So as it comes in here, with some probability, it'll be reflected back. And with 1 minus that probability, it'll get transmitted. Now this doesn't happen classically, right? Because classically it would just move through, right? It'll encounter a potential step and slow down, and that'll be it. But in quantum mechanics, you have to be careful because this is a wave-like phenomenon now that describes the particle motion. And so there's a portion of this wave that gets reflected back from the step. And you can calculate what that reflection probability is, what's the probability the particle gets reflected there, by calculating the ratio of the probability fluxes, which in our case, since they're just plane waves, it's just the magnitude of the wave squared, the reflected one, divided by the incoming wave squared, which is just 1. So that's the physics of it.
So nothing is being transmitted. Or what did you say? What do you mean by D equals 0 there?
What do I mean by what?
D equals 0. So you said no incoming particles.
That's because the particle is at infinity and it shouldn't exist on infinity.
Yeah, C is the that's right. Thanks, Sean. Yeah, so the C is the transmitted part. That's what gets past this barrier, and D we set to 0 because we don't want any source of particles out here. We're imagining shooting a particle. And the real thing is you have a wave packet out here, you shoot it in, and some portion of it will get transmitted and another portion of it will get reflected. So this is A. That's how we interpret the A portion of the solution. This is the B portion of the solution, and this is the C portion of the solution. So there's no D, because D would correspond to a wave packet out here coming in. So there's none of that.
Okay, so C represents transmission.
Yeah, C is transmission. Yeah. In fact, you can go back here and calculate the transmission probability, which is the transmitted flux divided by the incoming flux, which is the magnitude of C squared over A squared. And you can verify that it's going to be 1 minus the reflection probability. Right, because probability has to be conserved. So either the particle is going to get transmitted or it's going to get reflected. There's no other option. So the reflection probability is 1 minus the transition probability, the transmission probability. All right, more questions? And if you're ever in doubt, as I said, you could go in Mathematica and actually force it to solve the full time-dependent Schrodinger equation for you put a little step function for your potential. But this is how you would solve this problem by hand, I guess you could say. All right, so I'm going to clear this, if that's okay. And talk about bound states. All right, so, as we've been doing these things, this potential step, we know that, these funny solutions, the e to the plus or minus ikx, we know that they're not even in our Hilbert space, right? They're not square normalizable. So we always have to put them in some wave packet. But, and it makes sense because they represent like particles, coming from infinity and so on. But there are other kinds of states that we can look at, which are square normalizable, which are the bound states. And these are the true, they're the true states that satisfy the eigenvalue equation. They're the ones where this is really in their Hilbert space. And so they're square integrable. The wave functions are square integrable. And those are the bound states. Those are the true kind of states corresponding to particular fixed energies. And it's this square integrability that often leads to you not being able to choose any arbitrary value of E. You get quantization of the actual energy level. And I'll show you how that works. It's because unlike the incoming and outgoing particles where we can just kick them in with an arbitrary kinetic energy, now we have more conditions. We have more conditions on the wave function because we're going to ensure that it's square integrable. So what's a bound state? So we'll see. So a bound state might be if you have a potential, right, like this, and your energy is like out here somewhere, such that far away here, you'll get exponentially decaying solutions to your wave function. And so in here, you have oscillations. And in general, your wave function, looks something like this. And we'll see that, depending on, we don't always get solutions like this for any value of E, as we'll see. So the kind of most standard example in undergrad, I guess, is the infinite well, right? That's where V is sort of 0 everywhere. Again, red is V. And then you have V shooting off to, plus infinity at some barriers here. And let's say this is at 0 and then this is at A here as a function of X. So here it's V equals 0 from 0 to A, and then it shoots off to infinity. If it shoots off to infinity, what does that mean? That means like your exponential decay is like infinitely fast in here for any energy. So you basically force the wave function to go to 0 right away at X is 0 and A. That's what the potential shooting off to infinity would do. Otherwise, if it's finite, then you would have, the exponential decays. That part isn't so important, but in here, what do we get? If we have some energy here, E in here, right? In here, positive energy. Then in here, we'll get, oscillating solutions. The e to the I kx, the kinetic energy, where this would be the kinetic energy in here, and it'll be characterized by some k. And if we want it to vanish at these points, you can't just have any oscillations. The oscillations in here have to fit into the box. Otherwise, the wave function won't be continuous, right? So the boundary conditions here that psi is 0, they constrain our wave function. And so the solution really is going to be a sine of kx, where k, which is the kinetic energy, which is the wave vector associated with the kinetic energy inside the box, which in this case, since v is 0 in here, then it's just square root of 2mu over h bar squared. This can only take on particular values, because otherwise the boundary conditions don't work out. This won't vanish at 0 and A. And so the possibilities are, we can write them like this, right? Where n is 0, 1, 2, 3. So the boundary conditions for these bound states, right? They tell us that the wave function is to vanish at 0 and A. And so then when we try to match the solutions in here, which are the e to the plus or minus ikx, if you try to do that, what will happen is you'll get only certain combinations of them that work. And moreover, you have the k's, it only works for certain k's which ensure that the oscillations fit inside the box and vanish at the boundaries. And that's a common theme, is that when you look for these bound states and you try to match, what do you do here? Remember the boundary conditions. Psi is continuous, right? And also psi prime, the derivative over psi is continuous. And you do that here and here. And you see the difference. What's the difference for these bound states? We have an extra boundary condition, right? Remember before we had like incoming and outgoing stuff. Here we only have these exponential decays, right? Out here, so we kill the exponential increase over here on the left. So we have like an extra boundary condition or an extra constraint, right? And so remember that when we didn't have this constraint, we still found all the unknowns, A, B, and C. But this time we get even more constraints on the solutions. And this time, the constraint is on the possible energy values. So here for the infinite square well, you'll get constraints on the possible energy values, or equivalently a constraint on the possible k values. So that's very important. And in the homework, you see this on this current homework. You'll see this in the eigenvalue portion. In that homework, you get a constraint on you'll get. If you think about functions, say, of an angle, then you have to be sure that the function, is periodic in that angle. This is very similar to this kind of constraint where you force the function to vanish at the boundaries of some interval. This is like having fixed versus periodic boundary conditions, right? It's similar kind of boundary condition. It sets up a constraint, right? So you can compare this periodic condition versus our case where we set, psi at 0 and A equal to 0. So yeah, and and one last thing about this is that we have this A, the unknown here, that's set by the normalization, right? We have to ensure that the particle can be found somewhere. So you make sure it's square normalizable, it's square integrable. And you set the square of the integral equal to 1. So these are different kinds of states. They don't correspond to particles coming in from some source. They correspond to a particle having some particular energy and just sitting there at that energy. And so in this case, its wave function is a part of our Hilbert space. We don't have to interpret it in terms of a wave packet or anything funny like that. It's just the state of it. And so it's in the Hilbert space. And so it's square integrable. And so you can start imposing this constraint on the wave function, on the whole wave function. And how do you know whether or not you're in a bound state? Again, you just look at the wave function out at infinity. If you're ensuring that it decays to 0 out at infinity, that means all of the probability, right, of the particle being somewhere must be, near your region of interest, right? It must be like none of it is out at infinity. You don't have a source or a sink of particles out at infinity. So everything, the particle must exist somewhere, around x equals 0, inside the potential, essentially. So that's kind of how you can think about these 1, 2, and 3. You can think about these one-dimensional. Okay, any questions about that though? Take a little pause here to see if people are still following along, I guess. We good?
Do we
Yep.
really need that condition, the periodicity?
Oh, this is on the homework. Homework.
Oh, I missed that part. Sorry.
Yeah, no. It's just I'm just trying to connect it to what you do on the homework, where you're looking at these eigen. You like find the eigenvalues of d theta, right? And the space of functions is psi of theta. But remember that psi of theta, it's periodic, so that's a key point. All right, so good. So let's talk about this generally. This is general 1D wave mechanics. What do? Well, I mean, you set up your, you can generally set up 3 kind of regions. I call 1, 2, and 3. 1, 2, and 3. And you have some potential shape. And in here, the potential can do some crazy thing. And out here, there can be a variety of things, but we imagine it's typically constant. Maybe it's constant at infinity, so you like prevent the particle from going in here. Or maybe it's just, you have it 0. It's a common choice. We just 0 the potential out here. And so, and then what you do is you set up your energy, and you can look at the energy in different cases. Like you can have a positive energy or a negative energy. If it's positive, right, then we imagine if it's bigger than the potential, we have oscillating solutions. That means we'll get our non-normalizable little particles that are moving in from infinity or getting transmitted here. If the energy is negative out here, if it's below the potential, then we get the exponentially decaying solutions out here. And those are the bound states. And up here, we would get the scattering states. In almost any potential you can think of, you can sort of imagine it that way. Even something like, which I guess we won't have much time to do today, but even the classic potential, the parabola of the harmonic oscillator, right? X squared, 1/2 kx squared. We imagine again putting some energy here, and we ask, well, what's going on here? What are the solutions of the wave function going to look like? Well, out here, they should be exponentially decaying because the potential is going to be bigger than the energy. And in here, they'll get some, oscillations because it's got some, it'll be complicated, right? Because this is varying now. So, we can imagine slower wiggles here and faster wiggles in here because there's more kinetic energy. So there should be more, so you remember the wiggles, the wiggliness tells you, how much momentum you have. So there's more momentum out here in the center of it, right? So it should, should be lots of wiggles here, and then it kind of slows down a bit, and then here it's exponentially decaying. And we know these will be bound states. And we can immediately conclude that it's very likely that there will only be certain values of E, right, which will be allowed because there will be too many constraints on our solutions, and the extra constraint will constrain the different possibilities for E. And indeed, what we'll find is that E can only take on certain values. They're evenly spaced. And that's sort of what we'll look at eventually, maybe, I guess next time. But that's the kind of general scheme. And we can also think about, I want to say a little bit, okay, but any comments about the kind of general scheme? I'll do some of these, I'll do some examples in recitation, but I want you to kind of get in the habit of just thinking about these things in this way. Generally, you have some arbitrary potential, you stick in your energy, that's your eigenvalue of the Hamiltonian operator, and you just ask, what are the eigenfunctions? What do they even look like if they exist for that energy level? It's just worth thinking about that way. And then all you're doing is, when you're solving one of these problems, is writing out the general solutions in these regions, either exponentials or, oscillating exponentials, complex exponentials, and then you're matching. What are you matching? You're matching the psi. You're making sure it's continuous across any changes in the solution, and you're making sure that the derivative is continuous, and often it's convenient to do the logarithmic derivative, which is the derivative divided by the function itself. That's really how all these problems go, including the scattering ones and the bound state ones. It's just that in the bound states, you get one too many constraints, and you're like, uh-oh, I run out of coefficients to constrain. So the conclusion is that your eigenvalue is constrained. You can only take on certain values. That's basically how it works. So really, the harmonic oscillator, which often is taught, is sort of different from the infinite square. Well, it's not really all that different. It's just, this is a parabola shape, and the other one is just flat here and shoots off to infinity. But it's the physics of it is very similar. You're still looking for square integrable states, which are part of your Hilbert space. And because of that extra constraint, you get these square normalizable functions that decay at infinity in both directions. Then, you only get certain values for the energy. You get a quantization of the energy levels, which I guess is the original way that people thought about quantum mechanics, is a quantization of the energy levels. Yeah, I guess I won't quite have time to talk about this, but another point here is for scattering. We can actually say some general things, because, so here we have these scattering states, and we know if it's zero out here, the potential, then we know that out here, we have A plus A e to the ikx, right, plus B e to the minus ikx. Here we have some kind of solution, and out here we have so here we have, but it'll be two solutions, so it'll be C plus D. We might not know what these things are. They could be complicated functions inside this region. And then out here we have coefficients F and G, and I won't use E because E is the energy, but you have F e to the ikx and G e to the minus ikx, right? And this is the kinetic energy associated with this portion. And so next thing we'll do, I'll talk a little bit of one nice way to think about scattering is, however you're solving this problem using the matching boundary conditions, you can think about kind of mapping between the coefficients A and B and the coefficients F and G. Right, there should be some transformation I can do where this is a matrix, it's a scattering matrix M, where I can take F and G, right? I can do all the matching and everything from region 3 to region 2 and from region 2 to region 1. And I should be able to work out what M is. It should be some matrix, 2 by 2 matrix of some coefficients that, will depend on the potential. And I should be able to map out how to get from F and G to A and B, right? And that's what we'll do next time, is figure this out. And this will be related to something called the S matrix, which we'll spend a lot of time thinking about in the second semester. So that's what we'll do next, and then hopefully, we'll get through that pretty, reasonably quickly, and then we'll go back to the harmonic oscillator after that. So this is for next time. We'll do scattering. And then we'll go back to the harmonic oscillator. And in the notes, I included some more examples of like finite square wall and stuff. I'll do that in recitation, but I expect that people have seen, you know, how to solve finite square well and things like that, just from undergrad. And we'll do the harmonic oscillator in detail, but not going to spend much time. You know, I just did this very quickly, the infinite well, and could do the finite well. So I won't spend much time on that. Okay, yeah, I guess yeah. So it's that time. So any more questions? Any more comments about anything?
I just wanted to look at that, yeah, that picture on the right side, the bound states. So there is a energy level. Well, the energy level is not, the energy is quantized, right? So there are different levels there.
Yeah, but the procedure is the same as what I've been talking about. You pick an energy E, then you like figure out what the solutions have to be. Out here, it have to be exponentially decaying because the energy is, you know, bigger than the potential. And in here, you get some particle bouncing around, so they're oscillating solutions. And you can try to solve for this. And what ends up happening is that because the solution has to decay to zero far away, that introduces more constraints than you have then you have unknowns in your solutions. And so what happens, just like in this infinite square well, what happens is that you find that the energy itself is constrained to only, you know, have certain values. That's the only way to satisfy the condition that the wave function decays away at infinity. Here, it decays really fast. It just goes to zero right away, right? So that's like the extreme version of this. But, you know, the harmonic oscillator solutions also kind of look like that. You know, they decay to zero far away from the origin.